I'd like to go over some of the questions in the exam that seem to pose particular problems for many people. One of them we actually converted into extra credit. The other one is something that may come up again because it's comparing means using the t-test, and those of you that may be going on to use the t-test in your project may be interested in clarifying what you did wrong on a couple of those problems. So I'm going to start off with, let me see here. I'm going to start off with the problem on the interpretation of the margin of error that had so many people stymied. I think 3 people actually got it right, and it's a little bit. It's actually working backwards from the direction we usually take at this, but I think most of you, once you get a look at how we solve it, it'll make sense to you. Okay, so let's read the question. National Health and Nutrition Examination Survey assesses the health and nutritional status of adults and children. From 1999 to 2002, they sampled 2,712 men between the ages of 20 and 29, and they found that the mean body weight in the sample was 183 pounds. Okay, so we're dealing with a very large sample here, 712 subjects. It's a really large sample. So we're thinking that, that probably is a pretty good approximation of the mean of the population. Okay, it's actually the mean of the sample, but given that big a sample size, we're going to have some confidence that that's going to be pretty close. The margin of error associated with this estimate for 95% confidence interval was plus or minus 3 pounds. Well, let's back up 1 second and take a look at what that means. So that means that basically our 95% confidence interval, right, our margin of error was 3 pounds below that or 3 pounds above that. So in other words, 183 pounds plus minus 3 pounds, 180 plus 3 pounds. So we're 95% sure the true mean for the entire population is between 180 and 186. That's our 95% confidence interval. And we got that the usual way by adding and subtracting our margin of error. So let's take a look at what that margin of error looks like when we use it. We know that the way we calculate our confidence interval was we're going to take the sample mean plus or minus 1.96 times the standard error. Standard error is a distribution for that sample size of all the likely samples that we might get. Okay, in other words, this is not the standard deviation of the population. It's the standard deviation of repeated samples of size 712. Okay, so that whole thing is our margin of error. It's what we're adding and subtracting from our mean to get our confidence interval. Okay, so that's our margin of error. Now, we just said our margin of error was equal to 3, plus or minus 3. So we know that this whole part of the equation is equal to 3. So 1.96 times our standard error is equal to 3. Well, now standard error, how do we get that? Well, this is a very large sample. So our standard error is equal to the standard deviation of the population over the square root of the sample size. Well, in this case, we don't know standard deviation of population. We really don't know at this stage, do we? We know that the standard error is equal to standard deviation of population over the square root of the sample size, which is 712. Okay, so now let's see what we can derive from this. Let's substitute this in for our standard error. So we have 1.96 times the standard deviation of population over the square root of 712 is equal to 3. Well, now we got an equation that has only one unknown. Now, this is really kind of like we don't really know the population standard deviation. But we know that once we get into a very large sample size, we have a pretty good idea of what it is. So I'm going to assume that this is pretty close to the population standard deviation. So now how do we solve for that? One way we solve for that is by moving everything else to the other side of the equation. So 1.96 goes over here, and the square root of 712 goes up the top here. So our standard deviation is equal to 3 times the square root of 712 over 1.96. Okay, so let's solve that. I'm going to use my calculator to solve it instead of Excel. Okay, if I can find it, there we go. So let's first solve for the square root of 712. Let me clear everything. 712, square root of that number is equal to 26.7. Okay, and I'm going to multiply that by 3. And I got 80, and I'm going to divide that by 1.96. And that's equal to about 41 pounds. So I'm going to round that off for our purposes so we can get through this quickly and call that equal to 41 pounds. Now, that's an approximation of the standard deviation of the population. So let's go back and take a look at what our question was. The question was, assuming that the weights are normally distributed, what percent of individuals weigh between 180 and 186? Well, now we have a pretty good idea. We know X bar is equal to 183, and that's, we think, pretty close to the mean. And we have a pretty good idea what the standard deviation is. It's approximately 41. So now we know what our normal distribution looks like. I'm going to take this over to the next page, 183 and 41, and draw this as a normal distribution. So now we're dealing with our population, not the sample. 183 and a standard deviation equal to, what was it again, 41? I think it was 41, right? Yep, 41. So we're interested in what proportion of the population is between 180 and 186. So we're interested in this area in here. Well, in order to figure out what the area is in between these two segments, okay, we're going to use our normal distribution, our knowledge of normal standard normal distribution, to figure out what the area is from here down, right? So let's figure out what that. We know that this is 180. The mean is 183. So let's see what this is going to look like. So 180 minus 183. The z-score of this point, 180, would be 180 minus 183 over 41. Or in other words, it's going to be equal to 3 minus 3 over 41. So let's figure that out. Okay, so 3 divided by 41 equals 0.073. Z is equal to 0.073. Okay, so now let's go to our table or Excel or whatever other source you want to use to find it, to find this normal distribution. Z table. Okay, let's open this one. So a z-score of minus 0.07. Let's see where we are. There's 0.07, 0.0, okay, 0.00, 0.01, 0.02, 3, 4, 5, 6, 7 would represent roughly about, let's see, 0.72 would be a little bit, would start to get somewhere in between these two, 0.07, 0.08. So I'm going to call it 0.47. So this would represent 47.47 or 47% of the distribution of this population, right? 0.47. Okay, that means that this area in here must be, since the mean gives us 50%, this must be 3% in here. Well, if this area is 47%, if I go up the same amount to a z-score of plus 0.07, right? Well, then this area in here represents 3% also, and this area up here also represents 47%, right? Because this standard normal distribution is symmetrical. So we have 47% above 186 and 47% of the population below 180. So between the two, it leaves 6% of the population. Okay, and that's where our answer came from. If you go back and take a look at it, our answer turns out to be 6%. Okay, so if you got questions about that, email me. Maybe I'll find another way that I can explain it. But that's how we derived this thing. We started and we went back and we looked at what margin of error means. It means 1.96 times the standard error. We know the standard error is equal to the standard deviation of square root of sample size. We knew the sample size, so that left only the standard deviation as of the population as a unknown. So we're able to solve for that. Once we knew that, we could then construct a normal distribution and decide what percentage of the population was in the range that we were interested in measuring. Okay, so it's not exact, but we have pretty good confidence that that's going to be our answer. And certainly, out of the answers that we had here, that it's definitely the most reasonable answer. In fact, you probably could have deduced it. Like if you had, a lot of people wrote none of the above because assuming that you could not solve this equation, right? I think, or maybe you didn't want to spend the time on solving it because you were working on the parts of the problem. But you do have the information that you need to solve it, right? And the other two selections are so far apart that you probably could have even deduced that they weren't the first and second selections, yeah, right off the bat, because they just represent too big a portion of the population to be that likely. Because actually, they're more likely to be in that range if you're just looking at the sample distribution rather than the population distribution. Okay, so I hope that helps. The other thing that I noticed a lot of people had difficulty with was problem number 23, I believe. Let me see if I can't dig that up. Problem number 22, I'm sorry. Okay, so I'm going to open up problem number 22. And this is a problem which involves the calculation of the t-distribution from two samples. And this is something that's probably going to come up perhaps for your project, but certainly in the future as you continue on and work on some data sets for other courses or in the future. Okay, so let's take a look at this one. Psychologists would like to examine the effect of fatigue on mental alertness. The attention test is prepared, requires the subject to sit in front of a screen for 10 minutes, press the shutter button when a dot appears. A total of 110 dots is produced in a 90-minute period. The psychologist records the number of errors. He's interested in how often you get it wrong. Two groups of subjects, one that's limited to 4 hours of sleep, and the other one that's has a larger amount of sleep. So he's testing whether or not fatigue, one group is more fatigued than the other group, and he's testing to see if that influences their performance on this attention test, what he's calling an attention test. So let's take a look at what he's got for the two groups. He has 5 subjects that are limited to 4 hours of sleep, and the mean number of errors that they made was 34, and the standard deviation for the errors was 30. He has a second group which gets 8 hours of sleep, and he's got a somewhat larger sample size of 10, and the mean is 25. For that group, they have fewer number of errors. They got more sleep, so we're starting to lean that direction, aren't we? And the standard deviation is equal to 27. Okay, so we have two separate groups. So one of the first things that we know we're going to compare the means of these two groups, okay, because we want to know if the population mean for this group is really different than the population mean for this group. So in order to compare them, we know we're going to do a t-test. They're relatively small sample sizes, so a t-test is going to be appropriate here. So now we say to ourselves, okay, so I know my mean for my two populations, right? So now I have to calculate whether or not these means are far enough apart in terms of standard deviations for the samples, standard errors, in order for me to reject the null hypothesis. Okay, so my t-test is going to need, among other things, take a look at the formula for our t-test. Let's see. Let me see if I got it here. Here we go. Here's our formula for our t-test. Okay, we want to know, we know the two means, x bar 1 and x bar 2. We know the sample sizes. What we're missing now is a standard deviation for the population that we're going to use in this calculation. Okay, so now what are we going to use to calculate this? Well, in this case, we're going to use, it's going to be a pooled standard deviation. Why is it going to be a pooled standard deviation? Because the two standard deviations are very close to each other in value. And we have no reason to believe that the standard deviations of the populations are dramatically different. As a rough rule, if the standard deviations are less than twice what the other is, in other words, there's one is not less than half or more than twice what the other is, that we're probably going to want to pool the two standard deviations. Certainly in this case, they're close enough together that it's reasonable to pool these. When you use SPSS to calculate this, SPSS will actually help you with that calculation, that determination, because it'll run a test to determine whether or not the population standard deviations are significantly different or not. But in our case, they're very close together. We're going to do it manually, so we're going to pool these two values. So before we do our t-test, we have to determine a pooled standard deviation. And here's our formula for a pooled standard deviation. You've seen this before, I'm sure. This time I'm going to open up Excel so I can do these calculations a little bit more easily. Okay, let me reduce the size of this so we can see a couple of things here. Okay, so let's see what we need to know here. We need to know the sample size, right? Sample size for number 1, sample size for number 2. We want to know our standard deviation 1 and our standard deviation 2. Okay, so let's see what we have here. Group 1, sample size was 5, and the standard deviation of group 1, I believe, was 30. I'll go back and check before we actually work on. And for group 2, I think the sample size was 10, and the standard deviation for sample size 2 was equal to 27. Okay, so now I want to calculate a pooled standard deviation. I'm going to do this in 1, 2, 3 steps and then find the square root of them. Okay, so first thing I'm going to do is I'm going to calculate the first part of this equation. So that's going to be equal to our sample size minus 1, which is 4, equals 4 times our standard deviation squared for sample 1. So standard deviation for sample 1 is 30, so it's 4 times 30 squared, 30 times itself. Okay, I'm going to hit enter, and that's our first little part of that equation. So now I'm going to hit equal again, and I'm going to determine that second part of that calculation. That's going to be equal to sample size 2 minus, for samples 2, group 2 sample size, which was 10, minus 1 is 9, times the standard deviation of sample 2 squared. I realize I made a mistake there, so I'm going to fix it right here. Okay, hit enter. This is actually 27. Okay, and that'll adjust for us. Okay, some help from Excel. Okay, so now, next thing I need to know is the denominator of this equation. Okay, and the denominator of this equation is equal to the two sample sizes added together minus 2. So in this case, it's 5 plus 10 minus 2. 15 minus 2 is 13. That's our sample size at the bottom. So our pooled standard deviation is going to be equal to the square root of, and I'll start with the top, 3,600 plus 6,500, close these parentheses, divided by 13. Okay, so now to make sure that it does this whole thing, I put these in parentheses so it does the addition first. So I have to put the whole group into parentheses. So it finds the square root of the entire value. I'm going to hit enter, and our pooled standard deviation is about 30, right? It's 27.95. That kind of makes sense, doesn't it? Because it's somewhere between 27 and 30 makes sense. Our pooled standard deviation would be between the two. And it's actually closer to sample 2, group 2's standard deviation than it is to group 1. And that's also understandable too, because the sample size for group 2 was bigger than the sample size for group 1. So it kind of makes sense it would be closer to that one. So we have some confidence in this. So that's our pooled standard deviation. Okay, so now let's go ahead and calculate our t-value. Okay, so I'm going to open up that formula again so we can look at it. And that is going to be here. Okay. So our t-score is going to be equal to, it's going to be equal to t, let me scroll this up. T is going to be equal to, the top part of this is going to be the difference between the two means, which is going to be, let's see, the two means were What were the two means again? Let's see. Go back to the problem. We're 34 and 25. 34 minus 25 is going to be 9, right? It's going to be, okay. Divided by, right? Now, it's going to get a little bit more complicated now. In fact, you know what I might do? Let me again, I'm going to simplify a little bit. And what I'm going to do is first I'm going to determine what the top of this equation is, which is 9. That's x1 minus x2. And then I'm going to work on the other parts of this equation. So one part is the pooled standard deviation. Now the S1 is going to be our pooled standard deviation. Okay, is going to be equal to this times itself divided by the sample size for the first group, which was 5. Okay, the next segment of this formula that's under the square root sign is going to be equal to, this time it's going to be equal to, again, the pooled standard deviation times, divided by, pooled standard deviation times itself, divided by the sample size for that group, which was 10. Okay, now I'm going to actually calculate my t-value. Well, actually, let me do that square root first. Square root of the sum of these two values is going to be equal to this plus this. Okay, so that bottom part of that equation, the denominator of that equation, is equal to 15.5. So now our t-score is going to be equal to, the difference between the two means, which is 9, divided by the value of this, basically what's the standard error, pooled standard error for these two groups, which is going to be equal to 15.3. Okay, so our t-score is equal to 0.587. Okay, and let's see what we got. Let's see. Actually, there were a couple of other questions that we asked in here. Let me go through them stepwise. Calculate a pooled standard deviation. So there's our 27.96. You had a lot of leeway for error there, I think. Calculate a standard error for repeated samples from these populations. So this is our standard error, would be 15.31. And I think that's pretty close to, let's see where we got that. 15.31, there we are, there's our standard error. Okay, and then I think the next part is we asked for the actual t-score, calculate a t-statistic for the difference between these two means. And we actually calculated the t-score just here. And that's that last part of that problem. Okay, we didn't ask for a confidence interval and so on and so forth. We're actually comparing two means, so we're not actually using the confidence interval for this. We're actually comparing the two actual means themselves. So it's pretty typical of what you might do if you have an experimental study where you have two groups, and one group might be a placebo, one might be a drug group, one might be a placebo group, one might be a group that's been involved in a training session. The other group might not be. In this case, the two groups have varying amounts of sleep prior to doing attention test. Okay, so that's how we wound up solving that particular problem. Okay, so those two, I think, were the ones that a lot of people had issues with, those two particular problems. Now, the next thing I want to bring up, which I'm going to continue, I'm just going to do about half hour or so today, which I'm going to pick this up again on Saturday. And what I wanted to start off on is start to expose you to what we're going to be seeing in the upcoming weeks. Okay. Now, one of the things you're going to be working on is your project. You're going to be deciding on where you're going to obtain data for it, what kind of data you're going to work with. Now, so far, we have worked with basically only data that's numerical data. In other words, data that involves a scale, weight, blood chemical levels, blood hormone levels, blood sugar levels, blood pressure, so on and so forth. Okay. Unfortunately, not all the data that you're going to want to work with is necessarily numerical. Some of it may be categorical data. And one of the reasons I'm bringing this up is because we saw a really interesting source of data which was the New York City Department of Health, the annual health survey that New York City Department of Health does. Let's see, and it was called EpiQuery. I think you can actually find it by just doing a Google search. Here we go, EpiQuery. Okay, and I'm going to look at the community health survey for 2013. Actually, comes up by default. It comes up 2013. Let me wait for it to load. No, it didn't load completely here. Let me try it again. Load it again. Oh, is there something in the way of this? Nope. Try one more time. Let me close this and try this again. Okay, let's get it to load. My browser's having a little bit of a problem. Tell you what, let me change browsers. Let's use Firefox instead, or maybe Chrome. If you have a similar experience with Safari, you'll know that. Let's see if it is indeed the browser that it doesn't like. Oh, there it is. Must have been the browser. So you have a similar experience with Safari. Just use Chrome or Firefox. Let me try Chrome, just so we know that it works. Yeah, it's just apparently Safari that it's unhappy with. Okay, so let's examine some of this data. So here's a bunch of areas that we might be interested in, data that's stored in this community health survey. Now, there's ways to get this data out so that you can actually work with it in SPSS, SAS, and so on, and R, and so on and so forth. For the moment, I just want to actually take a look at it. Okay, so let's take a look here. Maybe I'm interested in influenza. Flu is coming up. Flu season's coming up here pretty soon. Haven't heard too much about it so far, but I'm sure we'll be hearing something about it pretty soon. Okay, so I'm going to go ahead and say I'm interested in the influenza vaccination rates in New York City. I'm going to choose that as the area I'm interested in the survey. Now, for the time being, I'm going to say unadjusted. I want just the raw data. How many people said they got an influenza vaccine? How many people said they didn't get an influenza vaccine? And I'm going to have to go ahead and say, go ahead, submit, and see what kind of results we get for this. And in fact, we get some pretty interesting results. We get some bar charts, which is really nice. Let's take a look at our numbers. 55% of the population that was surveyed said that they were that they obtained a vaccination. 45% said they didn't obtain the vaccination. Okay, estimated confidence is adjusted for age. I thought I clicked not adjust is unadjusted for age. Rounded in years. Confidence in business. Yeah, okay. I don't think this is the actual data. Well, no, I guess it is because there's more than that number of people in New York City. I'm amazed that they would have been able to survey that many people, but it may not be true in the other areas. Okay, so let's take a look. Let's say that this is legitimate numbers from New York City. 55% of these people were had an influenza vaccine, 45% didn't. Okay, so now let's take a look at this broken down by another category. Of the people who did or did not get vaccines, let's take a look at separating that data into another into another group. Okay, do I want to know by age group, ethnicity? Let's do it how about by whether a person is foreign born or US born? I think that's likely to give us, say, only two categories, so it's going to make it simpler for us for the moment. Okay, so now we could also break it down by another category as well within that. But for right now, I'm only interested in whether being foreign born or US born influences whether or not you're going to get a influenza vaccine in New York. So I'm going to click submit. And let's see what our results look like. Well, okay, we get bar graph again. Let's take a look at our numbers here. If you're US born, you probably 58% of the US born population in New York got an influenza vaccine, but only 51% of the foreign-born population got an influenza vaccine. Well, that's very interesting, isn't it? There is a difference between these two. And let's take a look at the confidence intervals. Well, the confidence interval for US born is 57 to 61. We're 95% sure that the true proportion for US born is in that range. And for foreign born, it's 48% to about 55%. They don't overlap, but they come awful close. And we know that we really don't use whether the confidence interval overlaps. That's not really a dependable way for us to make a judgment about whether or not we can say that there's a difference in the proportion between these two populations, right? So it is interesting they don't overlap, but now we have to take this a step further. Okay, so now, what would our null hypothesis be here? Okay, so I'm gonna pop out this information here into Excel. Okay, and for our purposes, I'm going to change these numbers a little bit. Oops. For our purposes, I'm going to change these numbers a little bit, make things a little simpler. And I'm going to say, let's see, U.S. born, foreign born. I'm going to add a row in here. Yeah, add a couple of rows. Okay, and whether or not they got a vaccine, vaccinated, not vaccinated. Okay, let's fill in these numbers here. And for our purposes, I'm going to make believe this is a smaller study and say that was 748 and 529. And for foreign-born individuals, it was 628 and 599. Okay, so that's where I picked up those two numbers from. And again, these numbers I think are extrapolated from smaller data set, but we'll figure that out later on. So right now I'm looking at a study where the total number of people that we studied was 2,504 people. Of those 2,504 people, okay, 1,200 were foreign born, and whoops, same number of foreign born, same number are U.S. born. Okay, so now, interestingly enough, it looks like the proportion of people that were U.S. born that got a vaccination is 58%, and the proportion of people who are not U.S. born who got a vaccination was somewhat lower than that. Whoops, I think I made some kind of mistake there. C4. There we go. Okay, so now I'm looking at this and I'm saying to myself, well, my null hypothesis here would be, if I'm doing a study, my null hypothesis would be that there's no difference in the vaccination rate for US born and for foreign born. So I would expect these two proportions to be equal. So I would say that P1 equals P2. P for US borns, proportion US born, equals the proportion for foreign born. My alternative hypothesis would be that the proportions are different, that P1 does not equal P2. So now I didn't go into this with any sort of idea whether one would be higher than the other. So this is going to be a two-sided test. So it's going to be that simple. The equality in the null hypothesis, P1 equals P2, and the inequality in the alternative hypothesis, P1 does not equal P2. So now we have to compare these two proportions to determine whether we can be 95% certain or have less than 5% chance that we would get this result if they were from the same population. In fact, they would get vaccinated at the same rate. So when we pick up on Saturday, we'll start to talk about how are we going to do this for categorical data, right? Which gives us a proportion when we were doing it mostly for numerical data in the past. Okay, and there's a couple of ways that we're going to actually wind up doing this. And they're going to involve something called odds ratio, relative risk, and something called chi-square. Okay, and as we move forward, these terms are going to start to make sense to you. You've probably seen these terms brought up in various studies that you've read, the abstracts of the studies where they talk about relative risk and odds ratio, or the use of chi-square to test a hypothesis and so on and so forth. Certainly, you've seen odds ratio probably quite often. Okay, so we're going to take a look at this, and we're going to determine how we're going to use these tests to determine whether or not we can reject on the hypothesis and say, for some reason or other, the foreign-born individuals aren't getting vaccinated at the same rate as U.S.-born individuals. Okay, so that's going to be really interesting. The real key here is that this is going to give us a mechanism to test categorical data, right? Categorical, U.S.-born, were they vaccinated? Yes, no. Are they U.S. born or are they foreign born? That's one variable with two values. Vaccinated, not vaccinated. Another categorical variable with two variables, yes and no. Right. So we're going to take a closer look at that. And it's going to come in particularly handy because so much of the data, if you want to wind up using it, so much of the data that we're looking at that's in the community health survey is categorical data. Like, for instance, I'm going to take a look at another one, diabetes. Okay, the result there is, do you have diabetes? The question was, have you ever been told by a doctor that you have diabetes? And the answer was categorical, yes or no. It's not a question, what was your blood sugar, where it's a numerical variable where we compare means. It's something that's a yes or no answer, which produces a proportion, 10% of its population, or 11% of its population was told they had diabetes. So now we might want to compare that to another population and see if it's different than another population. But again, categorical variable. So now we need a new mechanism for testing that, and that's what we're going to be working on as we move forward in the next couple of weeks. Okay, so I think that's enough for now. I'll post this so you guys can see it online, and we got a little bit of a review of a couple of problems that might come up again at some point for you guys from the homework, from the exam, and we got a little bit of a preview of what we might be working with going forward. So, see you again. Bye.